I was wrong, completely, utterly, devastatingly wrong about the fundamental nature of reality. And the most painful part, I knew it before I died, but my pride, my stubborn, relentless pride, wouldn't let me accept it. My name is Albert Einstein, and today I want to tell you about the most devastating moment in my intellectual life. The moment when a simple experiment, elegant in its brutality, shattered everything I believed about how the universe worked. You see, there's something they don't teach you in physics classes. Something so disturbing, so fundamentally unsettling, that most professors skip over it entirely. Right now, as you're watching this, particles in your body, particles that were forged in ancient stars, particles that make up your very flesh and blood, are instantaneously communicating with particles millions of miles away. Not sending signals through space, not transmitting information like radio waves, communicating immediately, faster than light itself, faster than anything I believed was possible. The taste of bile rises in my throat even now, decades after death, when I think about what this means. I called this phenomenon spooky action at a distance, and I spent the last 30 agonizing years of my life trying to prove it was impossible. I failed. The universe failed me, or perhaps I failed to understand that the universe owed me nothing. Not comfort, not familiarity, certainly not the courtesy of making sense. Let me take you back to 1927, to Brussels, to the most uncomfortable moment of my entire career. I can still smell the musty conference room, still feel the scratchy wool of my jacket against my skin as I shifted nervously in that wooden chair. The Fifth Soviet Conference. 29 of the world's greatest physicists gathered to discuss the new quantum theory. I should have been triumphant. My general relativity had explained gravity, predicted black holes, revolutionized our understanding of space and time. Instead, I felt like a man watching his life's work crumble to dust. Niels Bohr sat across from me, that infuriating, knowing smile playing at the corners of his mouth. His Danish accent made everything sound so reasonable, so measured, even as he described the most unreasonable universe imaginable. Werner Heisenberg hunched over his notebook, scribbling equations with the fervor of a madman. Max Born nodded sagely, as if the destruction of causality itself was perfectly natural, and they were all of them telling me that reality doesn't exist until you observe it. The coffee in my cup had grown cold, but I gripped it anyway, feeling the ceramic edges press into my palm until it hurt. "Nonsense," I said, and my voice cracked slightly. I cleared my throat and tried again, louder. "The moon exists whether or not we look at it. Particle has definite property, position, momentum, regardless of measurement." But Bohr leaned forward, his pale blue eyes twinkling with a damnable certainty. I wanted to reach across that table and shake him until that smile disappeared. Instead, I sat there, paralyzed by intellectual rage, as he spoke those words that would haunt my dreams. "Albert, my dear friend, before you measure a quantum particle, it exists in all possible states simultaneously. It is here and there, spinning this way and that way, alive and dead all at once. Only the act of measurement collapses this superposition into a single definite reality." I felt my chest constrict, my breathing becoming shallow and rapid. The room seemed to tilt around me. This wasn't physics. This was madness, masquerading as mathematics. This was the end of everything rational, everything beautiful about science. God does not play dice with the universe, I declared, slamming my fist on the table so hard that several coffee cups rattled in their sources. Bohr's response still echoes in my mind, more than 90 years later. He smiled, that gentle, devastating smile, and said softly, "Einstein, stop telling God what to do." The room fell silent. I could hear the ticking of the old grandfather clock in the corner, the distant sound of Brussels traffic outside, the rustle of papers as physicists shifted uncomfortably in their seats. In that moment I realized I was alone. These brilliant minds, these people I respected and admired, had all drunk the quantum poison. They had all accepted the unacceptable. For the next 3 decades I waged a private war against quantum mechanics. Not openly, I was too respected for that, too conscious of my reputation. But in the solitude of my Princeton office, surrounded by blackboards covered in increasingly desperate equations, I plotted, I schemed, I searched with the intensity of a man trying to save his own soul for a way to restore sanity to physics. The smell of chopped dust became my constant companion. My fingers were permanently stained white from scribbling equation after equation, trying to find the flaw, the crack, the logical inconsistency that would bring down the whole quantum edifice. My assistants would find me there at all hours, muttering to myself in German, drawing diagrams of impossible experiments, calculating probabilities that made my head spin. The weapon I chose was logic itself, pure, crystalline logic that had never failed me before. If quantum mechanics was correct, then it had to make specific predictions that could be tested in the real world. And if those predictions were absurd enough, surely they would fail when confronted with actual reality. In 1935, I collaborated with two younger colleagues, Boris Podolsky and Nathan Rosen. Podolsky was nervous, excited, clearly thrilled to be working with the great Einstein. Rosen was more skeptical, questioning every assumption. Together, in my cluttered Princeton office, with its smell of pipe tobacco and old books, we crafted what I was certain would be the death blow to quantum madness. I can still remember the exact moment the idea crystallized. It was a Tuesday afternoon, rain drumming against the windows, and I was staring at the equations on my blackboard when it hit me. A thought experiment so elegant, so devastating, that it would force physicists to choose between quantum mechanics and sanity. We called it the EPR paradox, though history has given it other names. Here's what Pre proposed, and I want you to really think about this, to feel the full weight of its implications. Take two particles that have interacted, become quantum mechanically entangled. According to the theory, they remain connected forever, linked by invisible quantum threads, no matter how far apart they travel through space. Now separate these particles. Send one to Jupiter. Send the other to Alpha Centauri. According to quantum mechanics, measuring one particle instantly determines the state of the other. Not after light has had time to travel between them, not through some hidden communication channel. Instantly. The moment you measure one, you know everything about its distant partner. I could smell the coffee growing cold in my Princeton mug as I worked out the implications, my hand trembling slightly as I wrote equation after equation. If this were true, if quantum mechanics really predicted such nonsense, it would mean faster than light communication. It would violate the very foundations of my theory of relativity. It would tear apart the fabric of causality itself. Either quantum mechanics is incomplete, I reasoned, pacing back and forth in my office until I wore grooves in the floorboards, or it leads to consequences so absurd that no reasonable person could accept them. There had to be hidden variables, secret properties, like tiny instruction sets written into each particle, predetermining how they would behave when measured. The appearance of randomness, of instant correlation, was just ignorance of these deeper classical realities. I published the paper with such confidence, such certainty. My hands were steady as I signed my name to what I was sure would be remembered as the document that saved physics from quantum insanity. Finally, I had cornered the quantum theorists. I had exposed the fundamental flaw in their reasoning. The scientific community would come to their senses. Sanity would prevail. They didn't. It didn't. For 30 years, 30 long, frustrating years, physicists largely ignored my challenge. They dismissed EPR as a philosophical curiosity, not a real physical problem requiring experimental resolution. They continued using quantum mechanics in their calculations because it worked, because it made accurate predictions. Never mind that it made no conceptual sense. The bitter irony ate at me like acid. I had discovered relativity by taking seriously the logical consequences of seemingly simple physical principles, yet these same physicists refused to follow logic where it led when it came to quantum mechanics. But in 1964, something changed. 8 years after my death, when I could no longer argue or object or rage against the darkness, a young Northern Irish physicist named John Stuart Bell picked up my challenge. Unlike the philosophers who had debated EPR for decades, Bell didn't just argue, he calculated. He did what I should have done, but somehow couldn't. He turned the EPR paradox into hard, testable mathematics. Bell derived an inequality, a simple mathematical relationship, that any theory with local hidden variables, any theory that respected the speed of light limit and the reality of particles, absolutely must obey. If my view was correct, if particles had predetermined properties and influenced each other only through local interactions, then experimental results would respect Bell's inequality. The numbers would add up in a particular way, bounded by the constraints of locality and realism. But if quantum mechanics was right, if the universe really was as strange and non-local as Bohr and his followers claimed, then Bell's inequality would be violated. The correlations between distant particles would be stronger, impossibly stronger, than any local theory could explain. The stage was set for the ultimate showdown between Einstein and quantum reality, between the universe I demanded and the universe that apparently existed. The first real test came in 1972 at the University of California, Berkeley. Stuart Friedman and John Clauser, two young physicists whose names I had never heard, but who were about to settle a debate that had consumed my final decades, built an apparatus that could measure entangled photons with unprecedented precision. Picture their laboratory, clamped and cluttered, filled with the hum of electronic equipment and the sharp smell of ozone from the high-voltage power supplies. Laser light fired through nonlinear crystals, creating pairs of entangled photons that raced away from each other at the speed of light. Photomultiplier detectors positioned carefully on opposite sides of the room, each one capable of registering the arrival of a single photon and measuring its polarization. Can you imagine the tension in that room as they prepared to run their first serious test? The weight of the moment pressing down on them. These two young men were about to settle a philosophical argument that had raged between giants, a debate that struck at the very heart of reality itself. Would the universe prove local and reasonable, as Einstein demanded, or would it reveal itself as fundamentally non-local, mysterious, impossible to visualize? The results, when they came, were devastating. Bell's inequality was violated, not by a little bit, not within experimental error, but decisively, repeatedly, undeniably. The correlations between entangled photons were stronger than any local theory, any theory that respected the speed of light and the independence of distant objects could possibly explain. I was wrong. The spooky action was real. But even this crushing blow wasn't enough for some skeptics, myself included, if I had still been alive, to object. Perhaps there were loopholes in the experiment. Perhaps the detectors weren't efficient enough, missing too many photons and allowing statistical errors to creep in. Perhaps the particles weren't truly separated, weren't really independent. Perhaps the desperate hopes of a worldview under attack. For another decade, physicists refined the experiment, closing loophole after loophole with obsessive precision. They improved their detectors, increased their separation distances, tightened their statistical analysis. Each improvement made the violation of Bell's inequality more pronounced, more undeniable. Then came 1982, and Alain Aspect in France conducted what many consider the definitive test. His experiment was elegant in its simplicity and devastating in its implementation. It created pairs of entangled photons using calcium atoms excited by laser light, then sent them flying in opposite directions toward detectors positioned 40 meters apart, far enough that light couldn't travel between them during the measurement process. But here's what made Aspect's experiment truly extraordinary. While the photons were already in flight, racing toward their respective detectors, he randomly switched the measurement settings. Acoustic optical switches, controlled by ultrasonic waves, changed the orientation of the polarization measurements faster than any signal could travel between the detectors. Think about this carefully, because this is where the true horror of quantum mechanics reveals itself. The choice of what to measure, which property to check, which question to ask of each photon, was made after the photons had already left the source, but before they reached the detectors. There was no time, even traveling at the speed of light, for any classical signal to coordinate their behavior. Yet still, impossibly, the correlations appeared. When one photon was measured as vertically polarized, its partner racing away at light speed, 40 meters distant, with no possible communication between them, somehow knew to be horizontally polarized. When the measurement angle was changed randomly, the distant photon instantly adjusted its probability of being detected at different angles, as if it could sense the change across space and time itself. The universe was non-local, fundamentally, irreducibly, impossibly non-local. But let me tell you what this really means, because the dry language of physics papers doesn't capture the full existential horror of it. When two particles become entangled, they don't just share information faster than light. They share existence itself. They become, in some profound and disturbing sense, the same entity distributed across space and time. Measure one, and you are not learning about a separate, distant particle. You're collapsing the single quantum system that happens to have parts in different locations throughout the universe. The appearance of separation, the comfortable illusion that objects are distinct and independent, crumbles away like sand castles before the tide. This violated everything I had believed about reality, everything that had made sense about the world. I had spent my life showing that space and time were intimately connected, that nothing could travel faster than light, that locality, the principle that objects are only directly influenced by their immediate surroundings, was fundamental to physics. Now quantum mechanics was telling me that locality itself was an illusion, a convenient fiction that broke down at the most fundamental level. But the experiments kept coming, each more precise than the last, each closing more potential loopholes, each confirming the impossible correlations with greater statistical certainty. Like hammer blows on the coffin of classical physics, they buried my worldview deeper with every test. In 2015, nearly 60 years after my death, physicists finally conducted what they called the perfect Bell test. Using random number generators seeded by observations of distant quasars, light from objects billions of light years away, emitted billions of years ago, long before Earth even existed. They removed the last possible escape routes for local realism. The logic was breathtaking in its thoroughness. If the measurement settings were determined by light from quasars billions of light years apart, then any conspiracy to fake quantum correlations would require a plot that began before our solar system formed. The universe would have had to plan the deception for eons, coordinating across impossible distances and timescales. The results were unambiguous. Bell's inequality was violated by more than 100 standard deviations. The chance that local hidden variables could explain the data was less than 1 part in 1031, a decimal point followed by 30 zeros before you reach a 1. Those are odds so small that if you wrote them out in full, the number would contain more digits than there are atoms in the observable universe. I was not just wrong, I was spectacularly, catastrophically, undeniably wrong. The most painful part of this realization is that I had the right intuition about incompleteness. Quantum mechanics, as formulated in my time, was incomplete, but not in the way I had hoped, not in the way that would preserve my sanity. The incompleteness wasn't in the theory itself. It was in my understanding of what reality could be. The universe is non-local. Entangled particles really do share instantaneous correlations across arbitrary distances, not because they're sending signals through space, but because the very notion of separate particles is wrong at the quantum level. What we call particles are simply localized excitations in quantum fields that extend throughout all of space and time. Think about what you are right now as you process these words. Your body contains roughly 1028 atoms, 10,000 trillion individual particles. Many of these atoms have been entangled with other atoms at some point in their history. In the nuclear furnaces of ancient stars, in cosmic ray interactions high in the atmosphere, in the chemical reactions that built your molecules. Some of those entangled partners are now scattered across the galaxy, embedded in distant worlds, perhaps even in other living beings. You are not an isolated, independent entity floating through space. You are a node in a vast network of quantum correlations that spans the cosmos. connected by invisible threads to particles throughout the universe. When you observe quantum phenomena in a laboratory, you're not just measuring separate, independent particles. You're collapsing probability waves that extend throughout space and time, affecting the quantum state of matter everywhere. Every measurement you make ripples through the quantum field, changing the fundamental structure of reality itself. This is what I couldn't accept, what drove me to spend my final decades in increasingly fruitless pursuit of a unified field theory. I was trying to restore locality to a fundamentally non-local universe, to impose classical order on a quantum chaos that didn't need or want my organization. But here's the deepest irony, the final twist of the knife. My own theory of relativity is what makes quantum non-locality so conceptually difficult. I showed that simultaneity is relative, that there's no universal now that all observers can agree upon. So when we say entangled particles correlate instantaneously, instantaneous relative to what reference frame? The measurement events don't have a definite temporal order in all possible coordinate systems. Yet somehow, mysteriously, quantum mechanics manages to be non-local while still respecting the principles of special relativity. The correlations are real and instantaneous, but they can't be used to send information faster than light or to violate causality. Nature found a way to be both impossible and consistent, to break the rules while still obeying them. Today, quantum entanglement isn't just a laboratory curiosity or a philosophical problem. It's the foundation of new technologies that would seem like magic to physicists of my era. Quantum computers use networks of entangled particles to perform calculations that would take classical machines longer than the age of the universe. Quantum cryptography exploits the fragility of entanglement to create communication channels that are literally unbreakable by the laws of physics. Scientists are building quantum teleportation networks, not to transport matter, but to transfer quantum information instantaneously across any distance. They are creating quantum sensors so sensitive they can detect gravitational waves by measuring the entanglement between individual photons. They are developing quantum radar that can see through any jamming or stealth technology by comparing entangled beams of light. We're building a quantum internet where information doesn't travel from place to place but exists everywhere simultaneously until observed. The spooky action I mocked has become the foundation of a technological revolution that promises to transform human civilization. But the philosophical implications remain as disturbing as ever. Perhaps more so. If locality is an illusion at the quantum level, what else might be? If particles can share existence across space, what does that mean for the nature of objects, of identity, of self? Perhaps consciousness itself is quantum mechanical, emerging from entangled networks of particles in the brain. Perhaps your thoughts and memories are distributed non-locally, spread across quantum fields that permeate all of space. Perhaps death is not the end, but simply a change in the configuration of quantum information that comprises your identity. I don't know. I died still wrestling with these questions, still profoundly uncomfortable with the universe stranger than I had ever imagined or wanted to accept. But I want you to understand something crucial. Being wrong profoundly, completely, devastatingly wrong about the nature of reality wasn't a failure. It was necessary. Science advances through the violent collision of ideas with experimental reality, not through the comfortable confirmation of our prejudices and expectations. Every theory, no matter how beautiful or intuitive, must eventually face the harsh judgment of nature. Most fail. Those that survive become stronger. I gave quantum mechanics its greatest challenge, its most formidable opponent. I forced it to prove itself against the most powerful arguments for locality and classical realism that could be constructed. Every Bayes test that violates the inequality I thought would destroy quantum mechanics actually makes the theory stronger, not because it defeats Einstein, but because it survives Einstein. My wrongness was productive. It led to new experiments, deeper insights, revolutionary technologies. It forced physicists to confront the most fundamental questions about the nature of reality. It showed that the universe is far stranger and more wonderful than any human mind, even one that had unraveled the secrets of space and time, could possibly imagine. So I ask you, here at the end of this confession, what are you wrong about? What deep convictions about reality, about truth, about the nature of existence might be comfortable illusions? What obvious facts about the world might crumble under careful examination? The universe doesn't owe you understanding. It doesn't care about your intuitions or respect your common sense. It simply is what it is, operating according to laws that may forever remain alien to human thought. And what it is we've learned through the quantum revolution I tried so desperately to prevent, is far more mysterious and magnificent than we ever dared dream. God may not play dice with the universe, as I once insisted with such foolish certainty, but apparently God does perform magic tricks that would make any conjurer weep with envy, illusions so perfect that even Einstein himself was completely, utterly deceived. And sometimes, perhaps always, being wrong about God's methods is the only way to discover just how amazing, how impossible, how beautifully terrifying the magic really is.